Good evening, students. It's Mr. Rich. It is Sunday, October 20th. It's time for another Mr. Rich Q&A. I've got a number of students that are here with us live, and I need your questions. So if you have questions that you want me to work, you need to submit them to me because I've got students here from all sorts of different classes. I've got some AP Calculus students here. I have some Algebra 2 students. I probably have some statistics students. And so I need your questions, right? Otherwise, I'm just going to like randomly pick a class and work some problems from that class just to keep things going. I do have one question that came in from Delta Math that involved geometric sequences. I'm not sure I know how to do this. It looks like a really hard question that would not probably be asked in AP Precalc, but you never know. College Board's pretty good at coming up with new ways of asking questions. So I am going to plop this up here and try to work it while I wait for your other questions to come in. Now remember, the reason I started this Q&A was really just to give you kind of just my students that I tutor an extra opportunity on Sunday night before you go back to class to ask me homework questions, like things maybe from the previous week that had you perplexed that we didn't cover in our session one-on-one, or something that you found over the weekend as you were working in Delta Math or an AP classroom or something like that. I'm going to share my screen and show you this first question that came through. That is the question. You can see it's from Delta Math. If you've ever worked in Delta Math, you probably recognize that as coming from Delta Math. Oh yeah, I see some questions coming through. That's what we want. Okay, this is the question. Hopefully you all can see this. It's about a geometric sequence. It says, find the 11th term of the geometric sequence shown below. So what I'm going to do is I'm going to show you how to write a geometric sequence. This might come in handy if you really have more SAT prep to do. You might need to know about geometric sequences. Usually it's arithmetic, I guess, though, on the SAT. But this is, let me shrink this up just a bit and zoom in on it. Okay. This is how we write geometric sequences. The nth term of a geometric sequence is any of the terms, that's what we call GK, any of the terms, times the common ratio raised to the n minus k. If you haven't taken AP Precalc, that might seem strange to you. If you are in AP Precalc, I hope it does not seem strange to you because that's the form. Now I'm going to show you how we use it, or what does it mean. What it means is that I can get an equation for the nth term of a geometric sequence by picking one of the terms and plugging it in for GK. Just stick it in there, okay? Whichever one you want. First one, second one, third one. Now, if I choose the first one, that means that this k right here has to be a number 1. If I decide to put the second term into GK, then I better put n minus 2 because I just put in the second term over here. So that's pretty straightforward. What's not maybe so straightforward is I need to know what R is. That's what we call the common ratio of the geometric sequence. It's the thing that you're multiplying a term by to get the next one. So if you tell me that this is a geometric sequence, and they have told us it is, that means that I can find the R by ratioing this term over the term right in front of it. I could choose this one over this one. It doesn't matter because the ratio will be the same. So I'm going to take negative 5x to the 13th over x to the 8th. And that, hopefully you see, is negative 5x to the 5th power. That would be the common ratio of this geometric sequence. So I'm going to plug that into our formula. So the nth term for this geometric sequence, and I'm going to use the very first term for my GK, is going to be x to the 8th. I will now put in my common ratio of negative 5x to the 5th, and my exponent is going to be n minus 1 because the x to the 8th is the first term. It's where n is 1. This second term is n equals 2. That's n equals 3. So keep in mind what that means. I could have, there's any number of equations I could have written to represent the sequence. I could have chosen the second term, which was negative 5x to the 13th. I could have put that here in the GK spot, same ratio, but now this exponent would be n minus 2 because I stuck the second term in for GK. But I'm not going to do that. I could. Why? I'm just going to use the first one. It's a little bit simpler. So let's get rid of this. Now I'm ready to find the 11th term. This is what we call the general equation that gets me the nth term of the sequence. They want me to get the 11th term. Okay, let's do it. G 11th term would be x to the 8th times negative 5 x to the 5th raised to the 11 minus 1. Let's just call that 10 because that's what it is. All right. I'm going over here to my TI-84. I could use Desmos, but I'm kind of sick of Desmos at this point tonight. So yeah, CS says negative x to the negative 5x to the 5th. Yes. Oh yeah. Okay. You're probably answering my question. Yeah, that's what that common ratio is. But now I need to take negative 5 to the 10th power. I know that's going to be positive, so I'm just going to take 5 to the 10th power. All right, when I raise a negative number to an even power, it's going to turn it positive. My goodness. So this is x to the 8th times, why do they do this to us? 976,000, or actually 9,765,625. Okay. And that would be x to the 50th power. Because when I raise a power to another power, I multiply the exponents. But now I need to multiply by x to the 8th. So that's going to be 9,765,625 x to the 58th power, because I would add those exponents when I multiply like bases. So I hope that's the right answer. I'm going to say I'm like 99% sure that that is the right answer on that. That is a weird question, but that's how we would do it using the concepts from AP Precalc. If you have any questions on that, or if I confused you somewhere, let me know while I pull up the next problem. I have some other ones that came in here to ask Mr. Rich at Gmail. All right. I like this one. I have a logarithm problem that came in. I think this is the problem. I'm going to write it down. It's kind of written out in text, but I think I know what it is. This looks like it's 2 times log. So whoever submitted this, let me know if that is right. Plus log. I'm thinking that might be log base 2. Something tells me it is. I have a feeling that this is 2 times log base 2 of x minus 7 plus log base 2 of 2 equals 3. It is log base 2. All right, good. All right, thank you, Caleb. Appreciate it. All right, so that's what we got. I'm trying to solve this for x. Well, a couple things that I'm going to do here. I'm going to evaluate this log right here. One of the things you want to know about logarithms is that if you have a match between the base of your logarithm and the base of the exponent inside your logarithm, and here's the general idea. Log base a of a raised to the b is just b. In other words, the base of the exponent matching the base of the logarithm, they cancel each other out. And it's just the exponent. That means this thing's equal to 1 right here, because this would be 2 to the 1 power. Log base 2 of 2 to the first power is the exponent 1. Now, I'll show you another, just as a side note, where that comes into play, right? If somebody is asking you to evaluate this logarithm, log base 3 of 27, and you're like, I don't know, how do I know what log base 3 of 27 is? Well, think about if you could write this number as a power of the base of the logarithm. And I can, right? 27 is 3 to the 3rd power. Oh, the answer is 3, like that. Okay. So anyways, I'm going to simplify this by saying 2 times log base 2 of x minus 7 plus 1 equals 3, but I'm going to move the plus 1 over and call it a 2. Now I'm going to divide by 2 on both sides because I have a 2 multiplier. If I understood that question right, I think there is a 2 multiplier out here. I'm going to divide by 2 on both sides, and I get log base 2 of x minus 7 is equal to the number 1. Now your teacher if you're taking college algebra or algebra 2, and they're teaching you how to solve this equation for x, there's one of two things they're going to tell you to do here. And I'm going to tell you the one that I don't recommend. Okay. They say, take this 2 base, move it to the other side. The number that's on the other side becomes the exponent, and then you leave the x minus 7. Now, does that work? Yes, that works. Okay. What you're doing is you are converting it from logarithm equation form to exponential equation form. You move the base of the logarithm to the other side. It becomes the base of an exponent. The other side shrinks and becomes the exponent. And then you get rid of the log, and it's x minus 7. So now you can see that the answer to this is x equals 9. That's the answer. Now, I'm going to show you the right way to do this, the right way to think about it, especially if you're going on to higher levels of math. When you are looking at this, you are thinking about logs and exponentials as being inverse functions. And in fact, the fact that they are inverse functions is why log base 3 of 3 to the 5th power is 5, because a log base 3 and an exponential base 3 knock each other out. So therefore, another thing that is true about logs and exponentials is if you have a raised to the log base a of b, then these two knock each other out. An exponential and log that have matching bases, base of an exponent, base of a log, with each other, they cancel each other out, leaving you, in this case, b. So really, the algebra move that you're doing right here is you are doing something that we call exponentiate. You are going to raise 2 power on both sides. That's really what we're doing, because these two knock each other out, leave me x minus 7. Here, 2 to the 1. Sorry, I didn't write that. As I'm exponentiating, I'm raising 2 power on both sides. That's a 2. I get x equals 9. That's the answer. Okay, hopefully that helps, Caleb. Next, let's see what else is out there. Got a few others. Uh-oh, another delta math. All right, I'm going to do one more of these geometric sequence problems. All right, I'm going to ask you, Carlene, did that last one work? Did you put that into delta math? I'm just wondering if that was the right answer that we came up with. Let me know, and I'll pull this other one up. There it is. All right, any of you calc students, let me know if you got a calc question. Yeah, find the 9th term. I won't take as long on this one. I'll try to whip through this. They tell me it's a geometric sequence, and they want me to find the 9th term, so I'm going to find the nth term formula using this. Well, the common ratio looks like it's 2x. If you take 16x to the 4th and divide it by 8x to the 3rd, you're going to get a 2x. So therefore, the common ratio is 2x. Let me check out my chat here. Where did my chat go? All right, it was correct. Okay, good. All right. Yeah, so I'm going to use the first term, right? 8x to the 3rd goes in for GK. That's my first term of the geometric sequence. The common ratio happens to be 2. And since I used the first term when n is equal to 1, then that means the exponent is n minus 1 to represent the first term. That is the first term of the geometric sequence. Now, if I'm trying to find the 9th term, I just say, okay, G9, the 9th term, is 8x to the 3rd times 2x raised to the 8th power. 9 minus 1 is 8. 2 to the 8th, 4, 8, 16, 32, 64, 128, 256. I think that's 256. So this would be 8x to the 3rd times 2 to the 8th, 256. All right, let's just make sure we don't give out wrong answers here. 2 to the 8th is 256 times x to the 8th power. And then I'm going to take 256 times 8, 2048. So I do 8 times 256, 2048, x to the 3rd times x to the 8th, boom, x to the 11th. I'm going with that. That's my final answer. All right, next. All right, I've got a bunch of sequence problems here, students. I'm going to be stuck here on AP Precalc unless I get some other questions coming in. I don't want to bore you all with AP Precalc questions. Okay, here comes another one. Let's see. Oh, they want an arithmetic. Okay, there it is. It says, use the graph to fill in an answer to the sentence below and find an explicit formula that matches the graph. Well, this is what we call an arithmetic sequence. Arithmetic sequences are what we call discrete linear functions. The dots form a line, but the function doesn't exist at the in-between points, right? The domain of this function goes, well, the domain is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and nothing in between. It's just discrete values of x, or what we could call n if we were talking about, we would usually use n, and we would usually use a sub n to represent the nth term of the arithmetic sequence. So what we will do is, yeah, right, it's an arithmetic sequence. So we want to find a function of n. So really what they're saying is assume that this is n as your variable. Well, an arithmetic sequence takes on this form. Right? The last two problems I was working here were geometric sequences, but the general term of an arithmetic sequence, a sub n, is the kth term. You get to pick which term you want to plug into this formula. The first, the second, the third, the fourth, it's your choice. I'll probably pick the first term, but I could pick any term. Plus d is the common difference, and then we do n minus k right here. So the things that I have to feed into this are I have to pick a term, and then I have to stick in here the number of that term. Whether it was the first, second, third term, I need to put in here 1, 2, or 3. That goes with the number of term that I stuck right there. I also need to know what we call the common difference, because arithmetic sequences have a common difference between the successive terms. But that is really the slope, right? If it's arithmetic sequences are discrete linear functions. So when I look at these dots, I need to know the slope between the dots. I can calculate this. This looks like it's going to be 1/2. If I do a rise over run between those 2 points, 5 minus 4 over 4 minus 2. 5 minus 4 is 1. 4 minus 2 is 2. So that means that this slope of that line, which is called the common difference, is a 1/2. There we go. So I'm ready to roll. I can say my function, they're calling it f of n. So instead of calling it a of n, the nth term, I'll call it a function of n would be, well, let's pick this first dot right here. That's at an n of 1. Well, that's like a 3.5. So let's go with one that we definitely know, 2. When n is 2, f of 2 is 4. So this is 4 plus 1/2 times n minus 2, because I chose to put in the second term when n is 2. So therefore the k needs to be a 2 to match that. That's it. I'm done. That's my, now I can find any of the terms. You want me to find the 100th term? Sure. Plug in 100 for n. Let's just make sure it works. Let's say, okay, does it work for the 6th term? F of 6. If it doesn't work, then I'm no good and we'll just shut her down and go home. But that would be 6 minus 2. 6 minus 2 is 4. 4 times 1/2 is 2. 4 plus 2 is 6. So yeah, f of 6 is 6. So that's the general, that would be the general equation that we would use for an arithmetic sequence. All right. Oh yeah. Uh-oh. I think we got some calculus coming up. Now my brain is really going to be taxed here. Okay. Oh my goodness. Here we go. Calculus. There it is. This says f of x. Sorry, just reading the text here from a student. Okay. All right. So this says f of x is natural log of x plus 4 plus e to the minus 3x. Yeah, that looks like f prime of 0. They want us to find f prime, the derivative evaluated at an x value of 0. Let me get my chat back up here. Okay. Well, I got to take the derivative, right? Before I can evaluate the derivative at 0, I have to find f prime of x. Well, we have to know how to take the derivative of a natural log function. There's a rule of derivatives that says this, that if you are going to take the derivative of a natural log, and we'll call it natural log of u, right? We use u just generally in AP Calc to represent some generic function of x. That would be, very simply, 1 over u times u prime. By the chain rule, I have to multiply by the derivative of the inside part of the log. But think about this, 1 over u times u prime is just u prime over u. So what does this mean? That when you're faced with taking the derivative of a natural log function, the natural log is going to go away in your derivative. And what you're going to do in your derivative is put the argument of the logarithm, right? When I use the word argument of the logarithm, the argument of a function is the inside part of the function. Like the argument, like if I write sine of x squared, right? The sine, this doesn't mean sine times x squared, right? It means the sine of the thing inside. That's the argument of the function. Well, it's the natural log of that thing. That's the argument. What I do is I just put the argument in the denominator, right? I don't change it. It's just x plus 4 plus e to the minus 3x. There it goes. Then on the top, I'm going to take the derivative of the thing that I just put in the denominator. I'm going to take the derivative of the argument. Well, the derivative of x is 1. The derivative of a constant is 0. And then the derivative of e to the negative 3x is itself e to the negative 3x, but then times the derivative of its exponent, which is a negative 3. That is the answer. That's the answer of f prime of x, I should say. Could I write it more neatly? Maybe a little bit. I could rewrite this as 1 minus 3 times e to the negative 3x, because I'm multiplying this e to the minus 3x times the minus 3. Typically, we would put the constant in front of the exponential. And since it's a negative, it would end up being a minus. All over x plus 4 plus e to the negative 3x. That is f prime of x. But they wanted us to evaluate this at 0. So f prime of 0 is 1. Now, I'm going to do some mental math here, class. E to the 0, right? When I stick the 0 in for x, it becomes e to the 0. E to the 0 is not 0. It's the number 1. Anything raised to the 0 power other than 0, but anything else, 0 to 0 is undefined, but anything other than 0 raised to the 0 power is the number 1. So this is 1 minus 3 on the top. Down here, 0 plus 4, that's 4, 0 plus 4. And again, e to the 0 power would be 1. This looks to me to be a final answer of negative 2/5, like that. Okay, Ella, I hope that was helpful to you. Going back to see what else came through. Uh-oh, more calculus. Oh no, I feel like this is going to be one that's too hard. Wait a minute, I already saw that one. Wait, hold on a second. Hey, Ella, it looks like, was it the same? Those look like the same problem. I think, Ella, you sent in the same problem twice. Oh, that was a multiple choice. I forgot that was, is that, hopefully that's, yeah, negative 2/5. That's it. I didn't even notice that was multiple choice. Oh, okay. Yep. All right, students, I don't see any others coming through. Let me look at the chat. Nothing. Any topics that you want me to go over? Just type something in chat that's bugging you from your class. We got time. Okay. Let me see who is here. Whoever has the greatest attendance, I'll do a problem in that class. How about that? I don't know. I'm seeing Precalc. Okay, find the function of parabolas using the vertex. Wow, the vertex or the directrix. Wow. Okay, I think we can do that. Hold on, let me go grab a problem. All right, I'm going to go grab a problem on parabolas. And while I'm doing that, somebody else post something so I know what to do after this one. I'm having to dig back into my archives here to find some problems here on parabolas and directrix. This is conic sections is what this is. Yeah, there we go. I think this is it. Yeah. Oh my goodness. These look like some good ones here. I don't know. It's been a while. I'm not sure about this. I'll give it a shot though. Okay. Let me see here. Yeah. Okay. I see it there, Caleb. Yep. That's a good one. That is a good one. Almost got it here, class. Yep. Got it. Share my screen back and let's do this. Going out on a limb here. Haven't done this in a while. Caleb, I think I can do it though. Let's go back here. This is what Caleb was asking about. Like, Suppose that we're told that we know the vertex of a parabola and we know the directrix. Now, if you haven't taken pre-calculus, which I think is probably everybody that's on here, other than Caleb, most of you are in pre-calc, but you haven't gotten to conic sections, parabolas as conic sections. So I'll show you what this is all about. Let's do we'll do number 25. The vertex is 4, 3. We'll do one with the horizontal it's y equals 7. Number 26. The vertex is at 3, 5, and the directrix is y equals 7. So here's what we're going to do. Here's the question. The vertex is at 3, 5. We know what that means, right? The vertex of a parabola. But there's something called a directrix of the parabola, and I believe that was at y equals 7. And our job is to come up with the equation of the parabola. And I'm going to first draw a picture of this because the picture, and I would recommend that you do this, Caleb, when you're working a problem like this, draw a quick sketch. You know, and it doesn't have to be perfect, but you would do something like this, even if it was on blank paper, right? I would just say, okay, I'll come out here 3, I'll call this 5. There's my vertex. The directrix would be 2 units higher up here at 7 on the y-axis, and it would be a horizontal line. Now, the reason why I would do that is because now I know that the parabola has to open downward, because the directrix is a line that's going to be above or below the it's gonna be on the side away from the opening side of the parabola. So that parabola has to look like this with the vertex here at 3, 5. Now, the general form of a parabola, when we're studying conic sections, for a parabola that's opening up or down, is going to look like this. It's going to be x minus h squared equals 4 times p times y minus k. Now, you may say, well, that's definitely not what I learned about parabolas. Yeah, I know. I mean, this is a different form. Okay, it is different. You're used to either standard form on parabolas or you're used to vertex form. It's something different. Now, what in the world is the p constant right here? That p is the distance between the vertex and the directrix. So this distance, this vertical distance right here is 2 from my picture, because the y coordinate of the vertex is at 5. Now, Caleb would probably be able to tell us that there's not only is there a directrix associated with a parabola, but there's also something called a focus that would be equidistant 2 units down. That would be right here. So the vertex is halfway between the directrix and what we call the focus of a parabola. The focus of a parabola, if you've ever seen a parabolic mirror or a parabolic satellite dish, they're shaped like parabolas because all the incoming radiation would bounce off of the parabola and it would be concentrated at the point of the focus. So if you see a satellite dish that's parabolic, or you've seen any of the if you've seen microphones on the sideline of a football game that are shaped like a round parabolic 3-dimensional shape, they'll have the microphone a little bit away from the inside. It'll be right there so that all the sound gets concentrated at that focus. But anyways, the p is that distance right there. So that is 2. So p is 2 here, and the h and the k is going to be the vertex. So this is going to be, it's very simple here. This would be x minus 3 squared equals 8 times y minus 5. That would be it, Caleb. Yeah, the latest rectum is going to be, if I remember right, I believe that is the distance across the parabola, if I remember that right. And that's going to be the 4 times p. That distance would be 8. Let me see if that's right. Hold on a sec. Yeah. So that distance is 8, 2p. No, I think it's 4p, because it's the latest rectum is the line segment that passes through the focus and is perpendicular to the axis of symmetry. It's a chord. So yeah, it is 4 times p. So I believe it's in this case that would be the number 8. This number should be the latest rectum. Okay. Anyway, so what I would recommend always, Caleb, is to sketch a picture of the information that they gave you. Okay, and then that'll help you figure out what you need to put into that formula. All right. I don't see any others that came through. Darn. All right. Let's see what else I can do. I still got about 15 minutes here, students. I don't want to waste your time here. I'll go grab something for the AP Precalc students. How about that? Yep. All right. I'm going to do a problem from 2.2. This is a problem I think I worked. Yeah, I worked a little earlier. I don't think we worked this one last night, but let's pull this one over. I know a lot of the AP Precalc students are having a quiz maybe this week on geometric and arithmetic sequences. So let's share this screen back. I'm going to work number 7 here. Here's what number 7 says. I'll go ahead and bore you all and read this out loud here. But this says, since being adopted as the national symbol for the United States in 1782, the bald eagle population has experienced large fluctuations. By the early 1960s, the bald eagle nearly became extinct. In 1963, there were only 417 nesting pairs of bald eagles in the United States. The population of bald eagles can be modeled using a geometric sequence, where 1963 represents year 0. In 2019, year 56, there were a total of 71,400 nesting pairs of bald eagles across the US. Based on this model, how many nesting pairs of bald eagles were in the US in 2000? So our strategy here must be, I have to come up with the general formula for the geometric sequence so that I could then use that general formula to estimate the nesting bald eagles in this particular year of 2000. And in order for me to come up with this general form, I got to know at least 2 years of data for the bald eagles. And they gave me that because in 1963, that's how many nesting pairs. And then in year 56, there were a lot more, 71,400. All right, so let's consider what they just told us. The 2 terms I know of this geometric sequence are 1963 was year 0. So in year 0, there was 417 nesting pairs. Then in the year 2019, which would be year 56, there's 71,400. Okay. And that's what I know based on this model. So the geometric formula looks like this. I've shown this to you already once tonight. And the GK and the K, no problem. I already know what I'm going to put in there. I'm going to put in 417 and I'm going to put in 0 because year 0, the 0th term, we'll call it. And, I think what I'm going to do here, though, the thing that is a little bit confusing about this, they call that year 0. I think I need to call this year 1. So in year 1, 1963, the first year that I have the data is 417 because in 2019, if you subtract 2019 from 1963, that is 56 years, 47. Yeah. So this has to be the first year. And this would then be the 50, because if I call that the 0th year, I think we have to do that. So I'm going to call this year 1. This would be year 56. I think when I worked this earlier, I left it at year 0. Okay, but I'm going to put in 417 for GK and I'm going to put in 1 for K. The question is, how do I find the common ratio? That's the hard part of a geometric sequence. Well, the thing that you got to remember about geometric sequences is that what you do in a geometric sequence to go from term to the next term to the next term is you are always multiplying by R. So in other words, to get from 417 to 71,400, I would be multiplying by R 56 times, and actually 55 times, because 56 minus 1 is 55. So it would be times R times R times R 55 times. So the equation that I would use to come up with my common ratio is I'm taking 417 and I would multiply it by R 55 times. That's called R to the 55th power. And when I did that, I would get to the bald eagle nesting pairs population of 71,400. That's what that's going to look like. I'm going to divide by 417. So I get this, 71,400 divided by 417. And then I would raise both sides to the 155th power. That's how I solve for r. So that's going to be r will be equal to this fraction raised to the 155th power. I'm going to actually do that over here. So I'll take 71,400. I will divide it by 417, and I will raise it to the 1 divided by 55. Okay, I hope you all are okay with the fact that I raised to the 155th. It's the same thing as taking the fifth root. I'm sorry, the 55th root on both sides. But the 55th root, which undoes the 55 exponent, it's the same thing as raising to the 155th power. So at any rate, that's my number right there. That is that's the multiplication that's done each year to get from 417 in year 1 to 71,400 in year 56. Okay, so that means then I could write my nth term to look like this. I'll use 417 as my G sub k, my first term. Here, I'm going to go ahead and I'm going to write this. I'm going to write this as the 55th root of 71,400. That's the exact common ratio right there. Okay, raised to the n minus 1 power, like that. Okay. Now, I need to know how many bald eagles were there in 2000. Well, which year is 2000 in this sequence? Well, if year 1 over here was 1963, then that looks like it's 37 years to year 2000. So my answer here would be, if I want to find the number of bald eagles in the 36th year, it would be G36. Did I get that right? No, 37th year, 2000, year 1, 1963. So we'll say 37 years later. So the 37th term is 4/17 times that number that's sitting over there on my calculator screen, which is the 55th root of 71,400 over 417, raised to the 37 minus 1 or 36th power. So to get my estimate of the number of bald eagles, I would take 417 times, and I'm going to go grab that full decimal, right? I'm not going to round this and introduce any rounding errors. So I'm going to grab that whole thing, which is the 55th root of that fraction, and then I'll raise that to the 36th power. So my estimate is that I've got about in that year, in the 37th year after the year 1, I should have about 12,081 nesting bald eagles right there. Pairs of bald eagles, I guess it was. That would be the answer right there. Now, to do a quick sanity check on this, if that makes sense, the one year that they told us in year 56, it was 71,400. So yeah, I definitely don't want to see a number bigger than 71,400. Now you may say, well, that's quite a ways away, but yeah, we're talking about exponential growth. So that kind of makes sense that in the year 2000, I could have 12,081. And then through exponential growth and by the way, what is the growth rate? If it's a multiplier of 1.098, that's about a 10% growth rate. That's what that is, right? Because that's about 1.10. So if you're multiplying something by 1.10 every year, that's a 10% growth rate. So with 10% growth rate, yeah, I could see it going from 12,000 to 71,400. All right, I'm looking over. Let me take one more look. I don't see anything in chat, but I'll go take a look at my inbox over here to see if there's anything else. I think there might be something over here. Nope, that was it. Well, students, that takes us to 9 o'clock. I'd go a little bit over if I had some questions. But anyways, thank you for coming, those of you that were here, and I hope you learned something tonight. So far, I've done this every week, I think, so far pretty much this quarter or this semester. So come back next week at 8 o'clock and we will do it again and come with some questions and I'll answer your questions to the best of my ability. All right, everybody, have a great week ahead and I will see you next time. It's Mr. Rich checking out. See you later. Thanks for coming. Thank you.